Can someone explain to me what's going on here?
Okay, look, I'm sorry. Tuesday has been slightly derailed thanks to Steve Mould attempting to do a simultaneous shorts.
Okay.
Sorry.
I have interesting facts about too.
I appreciate that, and I'm aware that was the request we sent, and this is a little off standard, but I think Katie has successfully brought us to what appears to be Brady's study.
Yes,
Where is Brady?
Where is Brady?
256 is in the house.
There we go.
It's me.
Brady, how you doing?
It's me. I'm very well. Thank you for joining me. Good. Thank you for joining me here on Number File 2, a very appropriate channel.
Yes, and so for everyone just coming in, Tuesday. Pretty exciting. And Brady, if you don't mind, I think Aliane had a fun fact about 2.
Please.
So, numbers are great, but I thought, what about shapes? We all know them, we all love them. 5-sided shapes, 4-sided shapes, 3-sided shapes. What about a 2-sided shape though? I think on Tuesday is the perfect time to celebrate a 2-sided polygon. And you might be thinking to yourself, hang on there, there's no such thing as a 2-sided shape. If you have 2 completely straight lines with an angle between them, they're going to continue on their merry ways and they are never going to come back round together. And to that I would say, you need to think a little bit outside of the box. And in this case, the box is the Euclidean plane. Other geometries are available. For example, this kind of elliptical geometry here, represented by the balloon. So if I take these 2 completely straight lines, and I'll just give them a little right angle, like this. Oh. So I've got two totally perpendicular lines, and I wrap them around this elliptical geometry here. I now have a shape which is made of 2 completely straight lines and has 2 angles, but is one whole shape, and this is called the Digon. And I actually love Digons so much that I thought I would get one permanently etched into my body. So you can see here I have a right angle tattooed onto my elbow, and this straight line comes all the way round, this one comes all the way round, and then they meet up at a nice happy right angle on the other side. This is also how, say you and your friend were at the North Pole, you can head off in different directions, walk underwater across some countries, and then by the time you get to the other side, you can meet up again at the South Pole. It's all happy. Now, some people say that Digons don't count as a real shape because they can't exist on the Euclidean plane. But I think on Tuesday, we should let Digons be Digons.
Nice.
We're up to 3 jokes now. So you've got a non-Euclidean elbow.
Yeah, well, I mean, I have a little bit more curvature than a flat piece of paper. I'm not an elliptical, not a Euclidean plane, so, yep.
I actually had, in my Things to Make and Do book, a picture of a Digon, but the illustrator did it incorrectly. And if I remember correctly, Steve Mould, you're the person who spotted that mistake.
Yeah.
There you go.
You should have left it in the book, then you could have put it into humble pie.
Yeah, I should have then used it as a mistake in the next one. Yeah, I hate to admit it, but Steve was the first person to find that one of many mistakes in my book. Well, we'll now move on. I think, Ben, you've got some number 2-ness.
Yeah, I'm happy to show you some number 2-ness. What I might do is make a little bit of writing material available. Are you seeing a canvas? I'm going to write the number that we're talking about. Can you see that?
Yes.
Can you correctly identify what number that is? Just checking. Actually, I want to talk about the square root of 2, which is famous for all sorts of reasons, but it has a lot of 2-ness about it. Famously, though, it's not a fraction. This is a fact you know, Matt, right?
Yeah,
so,
it's not rational.
But I can write it as a fraction, which is I'm gonna do a tiny bit of numerical wizardry and write this as a fraction. It's not going to be maybe a fraction that you're used to, but I'm going to write root 2 minus 1 and root 2 plus 1, and I'm hoping this is a sort of format that you recognise as the difference of 2 squares. In fact, that's going to be the square root of 2 squared minus 1 squared, which does actually, if you boil it all down, come to 1, which means I can define root 2 minus 1. If I divide both sides of this equation by root 2 plus 1, I get this. I'm writing in a different order for reasons which will become obvious in a moment. And I'm going to rewrite that by adding 1 to both sides. Root 2 is therefore equal to 1 plus 1 over 1 plus root 2. And this starts to feel a bit weirdly self-referential, but it's true, and you could check it on a calculator if you cared. I'm actually going to do one slightly odd thing and add another 1 to both sides, so I get 2 plus 1 over 1 plus root 2. And now I'd like to point out that this thing down here is the same as that thing over there, which means I could sort of swap in this self-referential definition into itself, which would mean that 1 plus root 2 is the same as 2 plus 1 over the whole thing I just wrote down, which is 2 plus 1 over the whole thing I just wrote down, which is 2 plus 1 over the whole thing I wrote down, which is 2 plus 1. I mean, I could scroll down for quite a long time here and keep going. The only annoying thing is this is not root 2 itself. This is 1 plus root 2, so let's just take 1 from both sides, and I get root 2 is the same as, to be in celebration of the two-ness, it's 1 over 1 plus 1 over 2 plus 1 over 2 plus 1 over 2 plus 1 over 2, all the way down. Yes, root 2 is 2's all the way down. And I just really like the fact that other square roots and radicals don't have the nice pattern. So the root 3 has not got 3's all the way down. It's actually got 1's and 2's alternating. But root 2 does have 2's all the way down. And if you like this sort of thing, the golden ratio gets a look in if you make those 2's 1's. But root 2 should be celebrated for its two-ness, I think, and particularly on Tuesday, I think.
So if it's 1's all the way down, golden ratio, 2's all the way down, square root of 2. What's 3's all the way down? I mean, again, this is Thursday.
Root 13 plus 1 all over 2. Or minus 1. And annoyingly, if you do root n and do the same sort of game that we've just done, or even say, just write it as 1 over n plus 1 over n all the way down and solve that with a nice little quadratic, actually. I did something similar on the number file video ages ago for the golden ratio, where we did this with the 1's. But try it for n and you'll get an annoying thing that only comes out nice for root 2, which is why we're celebrating the two-ness of it today, I think.
That's why 2 is amazing.
Too good.
And a fun bit of recursion. Although, you know, can backfire. I think that's our safe limit of recursion for the video.
Too much recursion, we're fine.
Hey. Still only 3 jokes. Okay, I feel like it would be rude to be guests on Brady's channel without Brady giving us some fine tuneness.
Oh, well, thank you very much. Look, I'm not as mathematical as you guys, and what I've decided to talk about is something that's very special to me, and that is Mount Everest. I'm sure everyone's heard of Mount Everest, highest point above sea level in all the world. It's a place very special to me, very dear to my heart, to the point I've actually been there 2 times appropriately. But today I want to talk to you about a bit of Mount Everest history, and that is how they decided how tall the mountain was. Because in the 1850s, the great trigonometric survey being run by British people in India was measuring the heights of all sorts of mountains in the Himalayas. And there was one mountain, it was called Peak 15 at the time. They didn't know how tall it was. And they set up all their theodolites and things and measured it from very far away. They were nowhere near this mountain at the time. And it spat out a number, and that number was 29,000 feet. And that made it the highest mountain in the world. They'd found the highest mountain in the world. But the problem was, the height was exactly 29,000 feet. And they didn't think anyone would believe this. It seemed implausible, or like it had just been rounded off. So the guy who was the boss at the time, the head of the survey, a guy called Andrew Waugh, decided to publish the number, but he added 2 to the height. He made it 29,002 feet, because he thought it sounded more plausible, more like a real exact height that they'd measured. This has become very famous now, and people talk about him being the first person to put 2 feet on the summit of Mount Everest. And that's such an old joke, it's actually in the Wikipedia article now as a famous joke. Right. So we have this 2 added to Mount Everest. But the story doesn't end there when it comes to adding 2 to Mount Everest. Because later on they remeasured, things got more accurate, and the accepted height was actually a little bit higher still, and they also flipped it over to meters, and for the longest time the height of Mount Everest has been known as 8,848 meters. Now, everyone's very familiar with this number. I remember when I went to Mount Everest at night, we got out our torches and wrote the number 8848 in the sky and stuff like that. But in 1999, the Americans, their geographic survey, they went to the top of Mount Everest with the GPS and decided to do a re-measurement. And they measured it at 8,850 meters. So yet again, 2 units had been added to the height of Mount Everest. And for a little while, this was the accepted height. 2 was added again. In more recent times, this has changed yet again. They've actually knocked it down a little bit to just under 8,849 meters. It's always changing. They're always debating about it. But I like this. I love Mount Everest, and I love that people just can't help adding 2 to its height.
And 8848, all the digits are powers of 2. I mean, that's...
Well, I mean, that of course, yeah, that's the main... I was hoping you'd pick up on that. That was my little Easter egg.
I was worried at the beginning that this was just going to be an excuse for you to show off that you've been to Mount Everest 2 times.
Well,
I'm glad it turned into more.
With, like, base camp, how far up for your
base
2
camp.
trips?
Yeah, I don't do the hard stuff. Yeah.
That's... that rounding error, like the illusion of not being accurate because it's a rounded number.
Yeah.
I think that there was some book that appeared in which discussed it just in passing.
Yeah. The thing with
it is a
when they
good
measured
story.
the 8,850 figure, the Americans, they actually published it with an error bar of plus or minus 2. They just love the 2-ness. It's the mountain of 2s.
It's 2s all the way down. It's 2s all the way up. 2s. And we've had Paul Grant joined us in chaos and is now. I said, hey, join in. Yeah. Bring a thing about the number 2. It's a nice, straightforward, simple video format.
I still don't know what's going on.
it's kind of the theme. But have you got us a 2s thing?
Well, so actually, I came in. I had this idea for what I would describe, which I knew for a fact I would explain poorly. It had to do with the notion of duality and how many layers of duality there are. But after Ben was talking, I realized there's maybe something better that I can talk about that also has to do with the root of 2 and recursion and things like that. So is it all right for me to share my screen? And
well, you weren't. Well, I've done that once and it backfired horribly. But let me see. 1 second.
All right. So we've got our Python open. I'm gonna import math because we're on number file 2. If we take
I take too much delight in import math as maths in Python.
Oh my god! Get out of this room! I don't care whose party this is. All right.
It's ambiguous at this point.
We'll do Matt Parker's. I'm a guest in the UK, so we'll do it. All right. So everyone
get too kind, sir.
So this is the square root of 2. Now, if I set that equal to the square root of 2 to the power of itself, we'll be taking 2 to the power of the square root of 2, right? And if we do that, I guess I should do that and then also kind of print out the value of x. It becomes a little bit higher. But then what if I did that again, where I said, hey, I want to take this value of x, this new one, which now looks like, 1.63, it's what the square root of 2 raised to the power of the square root of 2 happens to be. But I'm going to do it again. I'm going to take root 2 to the power root 2, which itself was to the power root 2. And then,
so you've got a stack of root 2s.
Yeah. Basically, yeah.
And you're working your way down.
A stack of root 2s. And actually, I can use the walrus operator, which you rarely get to use the walrus operator. No, it doesn't like that. Okay.
Well, that's why.
That's why. So we'll just kind of print it out. And so that should be the same thing as if I say maths dot root 2 to the power of maths. This is really hard to think about. Root 2 to the power of maths dot root 2. Did I do that right? No, math. Oh yeah. I was saying things out loud.
You generalized it. Yeah.
Okay, so there we go.
Hey, nice.
But let's keep playing this game. I'm just going to keep doing this so I get a bigger and bigger tower all along the way. So if I do it one more time, it should be a tower that's 4 high. So root 2 to the root 2 to the root 2 to the root 2. And you get 1.84. And if we just kind of keep playing this game and go over and over, and I say, for and in range like 100, let's do the same thing. What we end up getting is that it gets bigger and bigger and bigger, but it just constantly approaches the number 2. Don't worry about the numerical error stuff happening after that. It approaches 2. Eventually, this is in the limit as you kind of recursively go up. It's root 2 to the root 2 to the root 2. Like Mount Everest, it's just a mountain of 2s. You end up with 2, which I think is very apropos and beautiful.
Does that in any way link to the continued fraction? Or is this just a whole separate thing?
It feels very different, right? It's similar in that you've got an iterated function, because kind of what we're doing here, again, I haven't planned this, but if we try to think through. If my base here looks like the square root of 2, so 1.414 or something, the reason, Steve, like you would expect it to just blow up, like if I take 2 to the 2 to the 2 to the 2, that just grows insanely quickly. But if you think about what's happening, you start off at a value root 2, and then when you evaluate this function and kind of raise it to a power, so where would be? Root 2 would be like here. You go up to the red graph, and it's kind of saying for the value x that's root 2, we pop up to the red graph. And then if I just plug that back into itself, I say, oh, I want that now to be the input. I say, where do I go such that the x value is the same as that y value? So I kind of walk over just to the diagonal line to say, hey, currently this is my y value, I want that to be an x value. And then you do the same thing and evaluate the function. You go up, what you end up is kind of bouncing in this spider web towards wherever these graphs intersect. So if you're doing something like a base of something bigger, it does blow up, and it just blows up insanely quickly. But as soon as you get it to the point where those two graphs intersect with each other, you have it just bouncing towards a limit. And in our case, if that base happens to be exactly square root of 2, then that limit point happens to be exactly 2, which is such a beautiful little coincidence of numbers. And the continued fraction thing, you're doing a similar process where our function in that case, like if instead of b to the power of x, it was something like 1 over 2 plus x. I think someone in the comments, because I haven't prepared this, will correct it, like, no, that's not the right thing to plug in. But it would be something like this, where you're sort of iterating that process, and then your spider web will bounce you in towards one particular thing. And so if that base was, it'll be some sort of spider web related thing. But
it's
I
really
don't
nice
think
to see that the iterative, like an iterative construction of powers or fractions is actually the same as iterating a function. I think I had made that connection, but I've forgotten the connection. But a number you can think of as a function that's been iterated, and that's really helpful to see it bounce around.
Yeah, it's exactly.
I think that's
like
more
that.
similar to Katie's beer limits. Adding on a smaller part every time, you're just kind of bouncing closer to that limit.
I mean, I would think about it completely differently. So you've got all these root 2's going upwards forever, and if you call that little tower, if you call that x, then another way of writing that is it's root 2 to the power x. So that x contains that infinite tower of root 2's. So what's this x got to be? If you square that root 2 here, we'll get 2 on the left-hand side. So 2 would be a solution.
So the problem with that, James, is, so again, I'm just pilfering from previous YouTube here, do excuse me, but if you do that, it also works to say that it should approach 4. Because if you have this sort of recursive thing and you say, hey, I set it equal to 4, you could do all the same, and like x to the 4th equals 4. And then when you solve that, that would also be 2. And so then x should be the root of 2.
Crossed again on your graph diagram as well, right?
But that's not quite what's going on, though, because if you... In this case, we would be talking about when the base is root 2... oh, wait, no, you're right. God, here I am, so quick to be like, that's not what's happening, you idiot. No. Okay, so it is there. But the spider web will be... a lot more... it'll be divergent at that point. So if our initial value was something like 3, it will... It will kind of bounce back away from that one. So one of them is attracting and one of them is repelling. Exactly.
I have a question.
Yeah, let's go.
What does the exponent need to be so that those two curves only just touch?
That is such a good question. It's e to the power of e, or 1 over. It's like e to the 1 over d. It's something like that. Math.
E.
Yeah.
It's not E's day.
It's it's e to the 1 over e. So we'll have to wait until what is E day anyway? February 27th, February 78th. Yeah. We'll have to wait for the 78th of this month to properly celebrate that fact. Yeah, in America. Well, obviously this is the way to represent dates, is month and then day.
Obviously.
How do you represent time? Do you go minute and then the hour?
Oh, that's great.
All this chat about square roots has just reminded me of the worst fact about 2 that I found when I was looking up facts about 2 to decide what to talk about.
The worst fact?
Yeah, I mean, it's not a bad fact, it's just not as impressive as any of the other things. But, you know, when you've got, like, a square root or a cube root or a fourth root or whatever, 2 is the only number that you don't need to write next to the root, because everyone just knows what you mean. Like, it's too cool. You don't even need to write a 2, you just write the root symbol.
It's the implied root.
Hey,
look,
that is the worst fact.
This is very fascinating, and thank you very much for that, Katie. But Matt, have you seen what's going on over at your channel? Matt, it's out of control, man. Go and have a look at your channel right now. It's like...
What do you mean?
You took your eyes off the bowl. Go look at your channel. You've been faffing around here for hours. Go, 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 go. Go look.
Hang on. Let me... I'll share the screen for my channel.
Oh. Anyway, let's get away from the war thing. I'm more of a do unto others as you would have them do unto you kind of person. And the interesting thing about that is you can't really have a do unto others unless you have 2 people.
Dragged me away
so
from
the
this.
2
I'm going
people,
back.
like
Wait
being
here,
nice to each other,
this.
has a lot to do with how the golden rule works. So anyway,
hey, Destin, this is my channel.
Well, this is not your channel. You abandoned it, so it's clearly Smarter Every Tuesday now. And I mean, this is the first episode. You know the deal.
I did not abandon it. We're just all over on number file 2. Here, hang on. Let me share my screen. I'll show you.
Okay. I mean, but I showed up and nobody was. Whoa.
What's going on?
Oh, no, I think I opened a double recursion wall!
My God, it's full of 2s.
2's all the way down!
Sometimes a double recursion visual gag can spiral out of control, and when that happens it can take the whole universe with it, and only folks who are lucky enough to be on vacation and making an extra dimensional journey at the time notice it, and it's their job to read the credits. Thanks to Eugenie von Tunzelmann, who was convinced by Matt to render this whole thing, and to all the YouTubers who were talked into doing what was meant to be a simple Tuesday video. Links to all of them are down in the description, although they are now lost in an infinite recursion loop until someone resets the universe. Again.
Can you please just turn the universe off and on again?
I did it last time. All that remains now is to donate to WaterAid and wait patiently for Threesday Thursday.
Tom? Maybe try Alt F2 squared.
Every time.